Hi dear students, welcome to my PPT presentation on the topic cyclic groups. Very important theorem. Let G be a cyclic group. Then prove that G is infinite if and only if a power m not equal to a power n for all m not equal to n. Proof. Let G be a cyclic group. By definition, G is equal to set of a power n such that n belongs to Z, where a is a generator of G. Part 1. Suppose that a power m not equal to a power n for all m not equal to n. It is denoted by equation 1. Now we prove that G is infinite. Now we define a mapping f z to G as f of n is equal to a power n for all n belongs to Z. Let m comma n belongs to Z be two elements in Z. Then we have f of m is equal to a power n and f of n is equal to a power n. And consider f of m not equal to f of n. F of m not equal to f of n gives a power m not equal to a power n. That gives m not equal to n using 1. Clearly, f is 1-1 mapping from Z to G. Since Z is infinite set, distinct elements in Z having distinct images in G, clearly G is infinite. Part 2. Suppose G is an infinite cyclic group. That gives order of G is equal to order of A is equal to infinite. It is denoted by equation 2. Here A is the generator of G. Now we prove that a power m not equal to a power n for all m not equal to n. We can prove by contradiction. If possible, suppose that a power m equal to a power n for all m not equal to n. Without loss of generality, we can choose m greater than n. That gives m minus n greater than 0. It is a positive integer. Now a power m minus n equal to a power m into a power minus n. Since a power m is equal to a power n, that is equal to a power n into a power minus n, that is a power 0 equal to e. Since a power n equal to e gives order of a is equal to n, here order of a is equal to m minus n. It is a finite number. M and n are integers. It is a finite number. Since order of a is equal to infinite by using 2, so this is absurd. Hence our supposition a power m is equal to a power n is false. Therefore, a power m not equal to a power n for all m not equal to n. Hence proved. Theorem. Prove that nz plus is a cyclic subgroup of z plus where n is a fixed positive integer and z is the set of integers. Since z is equal to set of minus 2, minus 1, 0, 1, 2 and so on, then nz is equal to set of minus 2n, minus n, 0, n, 2n and so on. That is equal to set of np such that p belongs to z. Now we prove that nz is a subgroup of z. Let a comma b belongs to nz. Then a is equal to np for p belongs to z. And b is equal to nq for q belongs to z, since nz is equal to set of np such that p belongs to z. Now a minus b is equal to np minus nq, that is equal to n into p minus q, that is equal to n into x dash, where x dash equal to p minus q. P and q are integers, p minus q is also an integer. Since x dash belongs to z, nx dash belongs to nz. Therefore, a comma b belongs to nz gives a minus b belongs to nz, then nz is a subgroup of z plus. Now we prove that nz plus is a cyclic group. Since nz equal to set of minus 2n, minus n, 0, n, 2n and so on, that is equal to set of 0 plus or minus n, plus or minus 2n, plus or minus 3n and so on. This can be written as set of Pn such that P belongs to Z. This means all the elements of Nz are the multiples of N, then N is a generator of Nz. It can be written as SAND N. Therefore, Nz is a cyclic group generated by N and Nz is subset of Z. Therefore, Nz plus is a cyclic subgroup of Z plus, hence proved. We have proved that Nz plus is a cyclic subgroup of the group Z plus where n belongs to Z. Since Nz is equal to set of minus 2n, minus n, 0, n, 2n and so on, that is equal to set of np such that p belongs to Z, it can be written as sand n. It is generated by n where n is a generator of nz. For n is equal to 2, 2z is equal to set of minus 4, minus 2, 0, 2, 4 and so on. This can be written as sand 2. But 2 is a generator of 2z. Similarly, 3 is a generator of 3z, 4 is a generator of 4z and so on. Therefore, 2z, 3z, 4z and so on etc. are the cyclic subgroups of the group Z plus. These are examples for cyclic subgroups. Trivial or improper subgroups. Definition: let G be a group and E belongs to G, where E is the identity element in G. Then we have the singleton set E is subset of G and G is subset of G. These are two subgroups of a group G. Then these two subgroups are called trivial subgroups of G. All other subgroups other than E and G, if exists, are known as non-trivial subgroups. Example: we know that the fourth roots of unity G is equal to set of 1 minus 1 I minus I, where I square equal to minus 1 is a group. Clearly it is an abelian group. The subgroups of G are H1 equal to 1, that means E is equal to 1, identity element E is 1 in multiplicative group, and H2 is equal to 1 minus 1 I minus I, that is H2 is equal to G, and H3 is equal to set of 1 minus 1. These are three subgroups of a group G. Here H1 and H2 are two trivial subgroups of G, and H3 is 1 minus 1 is a non-trivial subgroup of the group G. Theorem: prove that any non-trivial subgroup of Z is isomorphic to Z where Z is the set of integers. Proof: let H be a non-trivial subgroup of Z. Since H is a non-trivial subgroup, by definition we get H not equal to set of E where E is the identity element and H not equal to Z. We know that every subgroup of Z is of the form Nz. Take H is equal to Nz for some n belongs to n. N is a positive integer. Now we define a mapping Fz to Nz as f of x is equal to nx for any x belongs to Z. It is denoted by equation 1. Let A comma B belongs to Z. A and B are two elements in Z. Then we get f of A is equal to Na and f of B is equal to Nb using 1. Now we prove that f is an isomorphism from Z to Nz. The first one is f is 1, 1. Let A comma B belongs to Z and f of A is equal to f of B. By using 1, f of x is equal to nx for x belongs to Z. Since f of A is equal to f of B gives Na is equal to Nb, that gives A is equal to B. Therefore, f of A is equal to f of B gives A equal to B, that is f is 1, 1 mapping. Second one, onto mapping. Let Q belongs to Nz. Nz is the codomain of f. Then Q is equal to Ny for y belongs to Z. It is denoted by equation 2. Since y belongs to Z, f of y is equal to Ny using 1. Using 2, Ny is equal to Q. It is Ny equal to Q. Therefore, f of y is equal to Q. Then we say that f is an onto mapping. This means every element of the codomain Nz having pre-image element in the domain Z. Therefore, f is onto mapping. Third one, f is homomorphism. Let A comma B belongs to Z gives A plus B belongs to Z. Since Z plus is an abelian group, by closure property, AB belongs to Z, A plus B is also belongs to Z. Now f of A plus B is equal to n into A plus B, that is equal to Na plus Nb, that is equal to f of A plus f of B. Therefore, f is 1, 1 mapping, onto mapping and homomorphism from Z to Nz. That gives f is an isomorphism from Z to Nz. This concludes that Z and NZ are isomorphic, hence proved. Theorem, prove that every isomorphic image of a cyclic group is again a cyclic group. Let G be a cyclic group and G dash be the isomorphic image of G. By definition of a cyclic group, we write G is equal to set of A power n such that n belongs to Z, that is equal to SAND A. Since G dash is the isomorphic image of G, this means there exists an isomorphism F from G to G dash which satisfies 1, 1, onto and homomorphism conditions. Since A power n belongs to G, F of A power n belongs to G dash. Since f of A power n is equal to f of A into A and so on n terms, that is equal to, since f is homomorphism, f of AB is equal to f of A into f of B, then we write f of A into f of A into f of A and so on n terms, that is equal to f of A whole power n. Since f of A power n belongs to G dash, f of A power n is f of A whole power n such that n belongs to Z. This means every element of G dash is the integral power of f of A, where f of A is a generator of G dash. It can be written as SAND f of A. Therefore, G dash is a cyclic group with generator f of A, hence proved. Thank you all for listening to me so far.